Artificial intelligence is huge right now, specifically deep learning, and it's fascinating what we're able to do with this. But if you think about it, deep learning can only interface with the data. The neural networks can't do much unless you give them the right data. This limits us in so many ways. The models aren't really thinking on their own. All they're doing is taking data and making some kind of pattern out of it. But now, with RL, we can actually create intelligence that can interact with the environment and make decisions from the experiences it gains being in that environment, similar to us. This is why I find it so interesting, and I think it's a key part to figuring out how to create artificial general intelligence. Now, I've always loved playing video games, and I've been recently creating a lot of AI projects. So naturally, I decided to create an AI algorithm or a DQN that could play video games better than me. Now, to understand how DQNs work, you need to know three main things. One is Q-learning, second one is reinforcement learning, and the third thing is how neural networks work. So, let's start with reinforcement learning. Reinforcement learning is pretty much a type of AI that uses a reward and punishment system. And the main goal is to maximize the reward they receive or the agent would receive. And there are four main components to this. The first one being the agent, the second one, the environment, the third one, the action, and the fourth thing, the reward. Now we model the agent as it interacts with an environment as a Markov decision process, or MDP. Now, these are mathematical frameworks for the decision-making process. To really visualize this and understand this, imagine a mouse is trapped in a maze. Now, in this maze, the end goal is to get to a big piece of cheese, which is waiting for the mouse at the end. Along the pathway, there are some traps and smaller pieces of cheese. Of course, the mouse is trying to avoid the traps, but also collect as many of the smaller pieces of cheese as it can. Now, in this example, we can think of the mouse as the agent. The different actions it could take would be moving left, right, going straight, or moving backwards. This would be the actions it could take. Different states or environment would be within the maze and where the mouse is within the maze. And then a reward would be where it wants to get at the final stage it wants to reach, the big piece of cheese. But it can also have negative rewards, such as moving into a trap. So now, being this mouse, what we want to do is trying to get at the big piece of cheese while collecting small ones, but not trying to hit any traps, and also make it there in the most efficient and fastest way possible. But you may be thinking, how does the mouse know where to go? Well, this is where Q-learning comes in. This is one of the solutions to the problem. At first, the agent has no idea what to do. Since it isn't supervised learning and the agent has no real past experiences, it doesn't know what actions to take in order to maximize the reward. So this is where the Q table ultimately needs to tell the agent what action to take to achieve the highest possible reward, at least for that state. Now, this is done through the Q-learning algorithm, which uses the Bellman equation. The Bellman equation pretty much states that Q values for a given state using policy prime is equal to the reward for the next time step plus the discounted future rewards from that point onwards. Now, let's imagine the mouse and maze example again. We initialize all the values to 0, so we don't have any values yet. So how do we know where to go? That's where the exploration-exploitation trade-off comes in handy. As the name indicates, this helps QTables decide whether to explore and try out new routes or to stick to the same old ones and exploit its benefits and rewards. Now, the most common strategy used, and the one that I use for the Atari games DQN, is the Espelon greed strategy. This means that we want to explore a lot at the start and slowly stop to the point where we only use one or two strategies. For example, if we set E to equal 0.05, we'll exploit the best variant 95% of the time and explore random alternatives the other 5% of the time. And this is actually quite effective in practice. Now, we usually start with a high epsilon, something like 0.99, and slowly decrease it to the point where the agent is only using the best policy. So like I mentioned, 0.05. Essentially, that's how Q-learning really is. Now, when it comes to DQNs, they're pretty much just Q-learning combined with neural networks. Since getting the Q values for every action state isn't scalable, we use a neural network to approximate these values. For our mouse example, the mouse didn't have too many options, so there weren't many Q values within that maze as well. But as games that get bigger, for example like the Atari games and the DQN I use, this simply won't work. There's way too many values, and approximating each different time step won't really make sense since there's so many values. Now, one of the things we do when making a DQN is we need to pre-process our images. So this means grayscaling the image to remove all the unnecessary things. We'll also stack the frames into 4, so our convolutional neural network can actually predict where the ball or object is moving. To really understand this, imagine two cars, or a picture of two cars. Now, when you first look at the picture of two cars, you can't tell anything. You don't know if the cars are parked if the cars are about to crash or if they're going to pass by each other. Now, let's say you get 4 photos of the cars or 4 frames of the cars moving. Now, from this, you can actually tell, is the car going to crash? Are the cars parked or are they reversing? Now, to build our DQN, we also need to add some sort of buffer. And this is actually called the experience relay. This helps us with 2 main things. One is reducing the correlated data. The second thing is better use of previous experiences. If you think about it, if we train the network in order from the first experience to the second one to the third one, we risk our agent being influenced by the effect of correlation. Since not much happens from frame to frame, the network's weights and bias can change and influence the agent's actions, and we don't really want this. So we'll have a replay buffer which at random will break this correlation and prevent actions from oscillating or diverging drastically. Essentially, the sample transitions are stored, which are then randomly selected from the transition pool to update the network. This stops one from data from being biased. So for example, let's say we're playing Pong and one of the agents keeps on shooting to the left corner. Now our agent kind of has a bias to stay near the left corner, and we don't really want this. So we'll take different replay buffers and experiences to make sure that correlation doesn't happen. We also need to stabilize the predictions or Q values that the neural network makes. Remember, with Q learning, we would explore all the states and determine the values, but with a neural network, instead we're approximating the values since we don't have the time to go through every value. To overcome the bias prediction, we calculate the TD error. This calculation states that the delta W, or the change in weights, is equal to alpha times the maximum Q value minus the current predicted Q value. This normalizes the values between our target model and our main model, making our main model more accurate in the end. Now, to sum up how a DQN works, we pretty much use a neural network to approximate Q values, which pretty much tells us how good it is to be in a certain state. We then use convolutional networks after pre-processing to figure out how and where objects are moving and how they're moving. The convolutional networks are also linked to a fully connected layer, which will then output the action our agent should take. We also try to use a replay buffer to avoid correlations and any biases the agents might have. We also use a loss function to calculate the temporal difference in order to find accurate Q values for our MDP framework. Now, with this model that I created, we can play many games like Atari Breakout, Tic-Tac-Toe, Ping Pong, and many more. And this model that I created was a somewhat simple model. With reinforcement learning, we can pretty much play any video game there is. And the fact that we can just drop an agent anywhere, in any environment, and have it figure stuff out on its own is so cool. And now reinforcement learning does have some limitations at the current time. For example, the high training times, as well as the few correlations that you'll see between the data. But the fact that it's so similar to how we think and work, I really think RL could be the key to achieving AGI in the future.